So we know that angular velocity has a vector quantity. So if you've got something and it's rotating like this, so it's rotating that way, then the angular velocity is going to be perpendicular to the rotation. So this would be angular velocity vector. So in other words, if you've got something and it's rotating in the screen here and it's rotating like that in the counterclockwise direction, the right-hand rule says that's pointed towards you. If you've got it rotating in the other direction, right-hand rule says it's pointing away from you. Now, notation here that I've got is a dot indicates something coming towards you, so it's out of the screen, and an X indicates something that's into the screen. Okay, and so that's going away from you. Now, as a student, I tried to remember that in 3 dimensions of vector, because you imagine that a regular vector to the right is like that. And so as a student, I used to think about it, well, it's like an arrow. And so you get the feathers in the back end of it. And so if it's coming right at you, you see the point. And if it's going away from you, you see the tail feathers. And so that's how I remembered it, as a little mnemonic to try to remember direction. Okay. So right-hand rule. Okay, so if you've got an object right here, some mass m, and it's moving with some velocity v, some r here, it's going around, we know v equals r omega, okay, and I exert a force on it, okay. Now, we already know I exert a force on it, F, that's going to accelerate it. So F equals ma, that equals mr alpha, okay. And we also know that if we have r times f, that's mr squared alpha, or in other words, if this is a system of things, it'd be the sum of the mr squared, so that'd be I alpha. Okay, and so this introduced us to the idea of torque, and we did this last chapter. But we also realized it's a little more complicated, because it's not just r times f, because if I exert a force in a different direction, it's only the component of the force in the direction that is perpendicular to r that matters. So that means the torque is going to be rf sine theta. Okay. Now, what's the direction of the torque? If I exert a force as illustrated here, so if I exert a force that way, then that means the acceleration is that way, which means the velocity is that way. It means angular velocity is as shown. Right-hand rule says that a force in that direction would result in a torque that is out of the screen. Okay. On the other hand, r's like that, if I exert a force like that, then that would make the velocity go around this way. So right-hand rule would say the torque is into the board. Now, why? Because the torque is I alpha. Alpha is rate of change of the angular velocity, but if the angular velocity is vector, so is alpha, the angular acceleration, which means therefore so is torque. So torque is a vector. So it's in or out. Okay. And it also matters, though, if r is this way and I exert a force up, that's going to be a torque, right-hand rule, okay, that tries to make it go this way, so that's a torque that is coming out of the screen. But if r is this way and I exert the same force, then that, the same force, so this force is still up, then that is trying to make it go the other way, and so that would be a torque in. Okay. All right. So it makes a difference which way r is pointing. So you can think of the r as a vector also. The force is a vector and r is a vector. And so torque is related to this. Now, again, we said, again, if r is like this and I exert a force that way, only this component of the force works, so only F sine theta. Okay, now, here's a really interesting thing that you get from Calculus 3, and that is something called the vector cross product. So if you had two vectors, A and vector B, and so let's say that vector A is like this and vector B is like that, okay, and I want to have the vector product. Now, we know that A dot B is going to be A times B times cosine theta. But there's another vector out there, A cross B, that gives you another vector. And the other vector is perpendicular to both of those vectors. Okay. If I get R vector and I get F vector, the torque vector is perpendicular to both of those. It's going to be in or out of the screen. And so that sounds a whole lot like the vector cross product. Well, even more so, because A cross B, the magnitude of that is A times B times sine theta. Well, that's exactly what you get for torque. Torque was R F sine theta. So that would say that the torque is equal to R cross F. Now here's the problem. Vector cross products. We have the vector A, we got the vector B, okay. Turns out that A cross B is not equal to B cross A. Okay. So the commutative law in which you interchange the two things does not hold for vector cross products. Now what's the problem? A cross B, the way you'd figure out the direction, because remember, this is going to be vector C. Vector C can be in or out of the board, or in or out of the screen. Either way is perpendicular. And so what you've got here is you got to decide. So it's the right-hand rule. Now the way that I do the right-hand rule for this is I take my right hand and I put it in the direction of vector A, and then I turn my hand so that my fingers point towards vector B. So if you lay your right hand lined up with vector A, and then you try to turn your fingers to point towards B, the only way of doing that, contorting yourself, is to actually to turn your hand so that your thumb points out. So A cross B points out. Whereas B cross A, if you put your right hand in the direction of B, you have to turn it so that in order to go from B to A, your thumb has to point in to the screen. So that would be the opposite direction. So that means that A cross B is equal to minus B cross A. They're in opposite directions. If R is like this and F is like that, R cross F points out, which is the direction that we said torque is supposed to go in this case. So that will be our definition of torque right here. And so now we have a definition, a working definition, vector definition as to how torque works. This turns out to be very cool and very interesting because of some things that it does. So we'll get back to that in a bit.